Welcome to Propeller Breeze, the show for student pilots, sim fans, and everyone chasing that first solo and beyond. All information in this podcast is for entertainment and general knowledge only. Always verify with certified flight instructors or regulatory authorities before attempting anything mentioned here.
Okay, so if you are anywhere in your private pilot training right now, you definitely know the struggle with the magnetic compass.
Oh, for sure. It's this weird paradox, right?
Yeah.
It's the only thing in the cockpit that actually knows where north is, but it's also maybe the hardest instrument to use when you're actually flying.
It's so frustrating the second you pitch up for a climb or roll into a turn or even just accelerate on the runway.
It goes crazy. It just starts swinging, it dips, it lags, it leads. It's just all over the place.
A nightmare, especially for a student trying to be precise.
It really is. And that's why we're doing this deep dive today. We're going to focus on the instrument that acts as your stable bridge to sanity.
The heading indicator, or the HI.
Exactly. The goal here is to really get into the nuts and bolts of how it works, but also, and this is key, why it has its own subtle flaws that you, as the pilot, have to manage.
Okay, let's unpack this. The mechanical marvel that frees you from the tyranny of that wildly spinning compass.
I like that. The tyranny of the compass. That's a perfect way to frame it.
So at its core, the HI is there because the magnetic compass just isn't reliable during flight maneuvers.
Right. The HI is designed specifically to give you a stable, easy-to-read heading reference for the short term.
Particularly when the magnetic compass is basically useless?
Precisely. The compass is trying to follow the Earth's magnetic field, which is actually pretty weak. So any kind of acceleration or gravitational force just completely overwhelms it.
But the HI is different. It's not magnetic at all, is it?
Not at all. It's a gyroscopic instrument. It's usually powered by a vacuum system or electricity, and it runs on pure physics, kinetic energy, and momentum.
Which means it's not affected by all that stuff that messes with the compass.
That's the key. You could put the plane into a steep, coordinated turn, and the HI should, in theory, stay rock steady. It doesn't care about g-forces or bank angles.
Okay, so hold on a minute. If the HI is so much better, so much more stable, why isn't it the primary heading instrument? Why do we still have to have that, that frustrating magnetic compass as the legal requirement?
That is the million-dollar question, and it gets right to the HI's biggest weakness, which is drift.
Ah, okay.
See, because the HI is purely mechanical, it actually has no idea where magnetic north is. It only knows which way it was pointing when you last set it.
So it only measures change.
It only measures change, exactly. The magnetic compass, for all its flaws, is the only thing that, when it finally settles down, is actually pointing north. The HI is just a tool to help you use that information more easily.
So the HI is your stable working tool, and the compass is your ultimate but shaky reference.
You've got it. That's the relationship you have to internalize as a pilot.
All right, let's get into the physics then. This is where it gets really interesting for me. What makes a spinning piece of metal suddenly so smart?
This is all about a core principle called rigidity in space. So picture this. Inside the instrument case, there's a heavy little rotor, a wheel, that's spinning incredibly fast. We're talking tens of thousands of RPMs.
Wow.
And it's mounted in these things called gimbals, which lets it pivot and move freely in any direction. When that rotor gets up to speed, its own momentum makes it want to resist any force that tries to change its orientation.
So it's like once you get it spinning in a vertical plane, it just wants to stay perfectly vertical no matter what.
Exactly. And here's the aha moment. You're not actually turning the gyro when you fly.
What do you mean?
The gyro stays fixed, rigid in space. What's actually happening is that the aircraft, the instrument panel, the casing of the HI, is rotating around that stable spinning gyro.
Oh, that's cool. So the compass card that I'm looking at is attached to the gyro.
Yep.
And the little airplane symbol is attached to the instrument case. So when I turn left, the case turns left around the fixed card?
That's it. It's an incredibly clever mechanical solution.
Uh-huh.
You use kinetic energy to create a fixed reference point, and then you just measure your own movement against it.
Which is why it's so stable in turbulence. The plane is bouncing around, but the gyro is just sitting there holding its position in space.
Right. But, and there's always a but, it's not perfect.
Right. We mentioned drift. The instrument slowly kind of creeps away from the heading you set it to. This is why instructors are always yelling, check your HI.
They are, and for good reason. And the sources point to two totally separate reasons for this drift. One is simple mechanical friction. The other is, it's Cosmic.
Cosmic. Okay, let's start with the mechanical one first. You said friction or precession. How does a little bit of friction inside the instrument cause the heading to drift?
This is where gyrophysics gets a little weird and counterintuitive. It's a property called precession.
Okay.
So if you have a spinning gyro and you apply a force to it, so you push on the top of it, it doesn't tilt away from your push. The effect of that force actually happens 90 degrees later in the direction of rotation.
That's bizarre. So if I push down on it, it actually tilts sideways.
Exactly. So now think about the tiny constant forces inside the instrument. Worn bearings, a little bit of dust, even air resistance.
Right, microscopic forces.
These tiny forces are constantly pushing on the rotor. And because of precession, the rotor doesn't resist them directly. It yields 90 degrees away, which causes its axis to slowly, steadily tilt.
And that tilt is what we see as the heading slowly creeping off.
That's the drift. And if the instrument is old or not well maintained, that drift can be really bad. You might have to reset it way more often than the standard 15 minutes.
Okay, so that's the mechanical error. It's basically wear and tear. But you mentioned a cosmic error.
I did. And this is the really mind-bending one. Even if you had a mathematically perfect, totally frictionless gyro, it would still drift.
Ow.
Because the gyro is holding its position rigid in space. But we are flying on a planet that is rotating through space underneath it.
Oh, okay, say that again.
The gyro stays pointed at a fixed spot in the universe, but the Earth is spinning. So, from our perspective on the moving Earth, it looks like the gyro is drifting. We call this apparent drift.
So the error isn't in the instrument, it's in the planet.
That's it. The Earth rotates at 15 degrees every hour. So, even with a perfect instrument, your HI will appear to drift by as much as 15 degrees for every single hour you're in the air.
15 degrees an hour. Okay, let's put that in pilot terms. You're on a 2-hour cross-country flight. If you never reset your HI, by the end of it, you could be off by 30 degrees.
You could. And if you're aiming for an airport 50 miles away, a 30-degree error means you're going to miss it by, I don't know, dozens of miles.
That's not just an inconvenience. That's a serious problem.
It's a huge safety issue. So that constant predictable 15 degrees per hour drift plus the unpredictable friction drift. That's why you have to keep cross-checking with the magnetic compass and resetting the HI.
You're manually correcting for the motion of the planet?
You really are. When you reach over and turn that little knob, you're not just adjusting an instrument. You're resyncing your little fixed point in space with the magnetic field of a spinning Earth.
That's a much cooler way to think about it. So, given that this is a constant chore for pilots, what's the modern solution? I mean, an airline pilot isn't resetting their heading every 15 minutes, are they?
No, they are not. And that brings us to the modern fix, which is slaved systems.
These are usually part of what we call an HSI, or a horizontal situation indicator, right?
Exactly. The HSI is a much more advanced display. But the key is what's happening behind the scenes. A slave system basically does that pilot cross-check for you automatically and continuously.
Okay, so how does it do that? Where does it get its magnetic north information from?
It gets the signal from something called a magnetic slaving transmitter, but everyone just calls it a magnetometer.
And this isn't just another compass.
No, it's a very precise electronic sensor. And crucially, think about where it's located. It's usually mounted way out in a wingtip or in the tail.
As far away from the engine and all the electronics as possible.
Right, to get it away from all the magnetic interference that messes up the compass in the cockpit. So the magnetometer gets a really clean, accurate reading of the Earth's magnetic field.
And it sends that signal back to the HSI.
It sends that signal to a little computer, a comparator circuit. That circuit is constantly looking at two things: what the gyro says the heading is, and what the magnetometer says the heading really is.
And if they don't match?
If it sees the gyro starting to drift, it sends a tiny electrical signal back to the gyro that physically nudges it. It torques it back into alignment.
Ah, so it's constantly making these little automated corrections.
All the time. So these slaved systems, they generally need no adjustment at all from the pilot. They automatically correct for both the mechanical drift and that cosmic Earth rotation drift.
Which frees up the pilot to, actually fly the plane.
And that's the whole point. It takes a tool that needs constant babysitting and turns it into a permanent, accurate, and stable reference for navigation.
So, to bring this all home for you, the student pilot, understanding this stuff really matters. Knowing that the HI is stable because of rigidity in space, but that it's constantly fighting two enemies, friction and the actual rotation of the Earth, that's what makes the procedure make sense.
It really is. When you look at that little knob on a simple HI, you realize you're not just fixing a number. You are actively participating in the navigation. you're compensating for planetary motion. That's the difference between hitting your next checkpoint perfectly or being miles off course.
Absolutely. Okay, so as we wrap this up, let's leave you with a final thought to chew on. We've established that the heading indicator's stability comes purely from the physics of a fast-spinning rotor.
It's just that kinetic energy.
So, with that in mind, what is the single most critical check a pilot has to perform right after starting the engine? And why does that mechanical reality make the HI completely useless without that one initial setup?
Think about it. The engine starts, the vacuum pumps spin up, the gyro gets its rigidity, but it becomes rigid pointing in a completely random direction. Until you do that first alignment with the magnetic compass, that stable heading it's showing you is stable, but it's also completely wrong. What happens if you forget? Something to think about on your next pre-takeoff check.
A great point to end on. That's a wrap on our deep dive into the heading indicator. Fly safe and keep those instruments synchronized.
That's it for this episode. Keep your wings level, your brain sharp, and catch you next time in the pattern. Thanks for riding with Propeller Breeze.